In this lecture, we are going to discuss about sufficient condition for a function to be analytic. First is a statement. First is a statement of the sufficient condition. The single valued continuous function fz is analytic in a domain D if the four partial derivative ux uy vx vy are exist are continuous and satisfy Cauchy-Riemann equation at each point of D. Proof. That is single valued continuous function. If all the four partial derivatives exist and satisfy CR equation, then the function fz is analytic. This is the sufficient condition for a function to be analytic. Now we are going to prove this one. Given w equal to fz and fz is the function of u x y plus I b x y. U is the function of u x y. If we given a small increment to u, then delta u is equal to u. We give small increment to the value of x, delta x, y, value of delta y. Therefore, u plus delta u minus u, that will be delta u will be the u plus delta u minus u, that is this minus this one. Therefore delta u will be my u x plus del x comma y plus del y minus u x comma y. Now next I am adding and subtracting a term from this equation, right hand side of the equation, then it will not create any change. That is x plus delta x y. Then I am adding u x plus del x comma y minus u x comma y. This cancel out and we will left with this right hand side of this equation. Then we rearrange the term, put a bracket here, put a bracket Then by mean value theorem, if f is a function in the interval defined in the interval a plus a h, continuous in this interval, differentiable in the open interval a plus h, then there exists theta lies between 0 and 1, theta lies between 0 and 1 such that f takes a plus theta h is equal to f of a plus h minus f of a divided by h. So here u is a function of x, y, continuous, having partial derivative which are continuous in the given domain t. So there exists theta, u is continuous, partial derivative exists, so there exists theta lies between such that theta lies between 0 and 1, 0 and 1 such that u, y, here increment is given to the y variable, increment is given to the y variable, so it will be partial differentiation of u with respect to y, as u is a function of x and y. So here this is x plus del x, and y increment is given to theta 1, here I am taking theta 1, this is theta 1 delta y. Then here it is, here my u, here my interval will be y plus del y. Okay, so del y, this is the interval, so this is u x plus del x, y plus del y, minus u x plus del x, y by delta y. In the next step we cross multiply it, it will goes to here, this del y will goes to left hand side, and we will left with this one. That is value of this will be my this one, del y uy x plus del x, y plus theta 1 delta y. So put this value, so this value will be my delta y uy x plus delta x, y plus theta 1 delta y, then plus this portion, here my increment is given to x variable, so this will be delta x. Looking at this, we can write u x, then here x theta 2 delta x comma y. So erase this portion, put this equation 1, then write where theta 1 lies between 0 and 1 and theta 2 lies between 0 and 1 by mean value theorem. Okay, since uy and ux partial derivative are continuous, therefore they are uniformly continuous. Since ux and uy are continuous, therefore they are uniformly continuous, and therefore therefore by definition of uniform continuous, this is the DEFN stand for definition. Therefore by definition of uniform continuity, we have ux and uy are continuous in domain D. Therefore by definition of uniform continuity, we have, if what is uniform continuity? If f is defined in an interval I, then f is uniformly continuous. If for epsilon greater than 0, there exists delta greater than 0, such that f of x1 minus f of x2 less than epsilon whenever x1 minus x2 less than delta, where x1 x2 belongs to the interval I. That means for each small interval we will get some delta corresponding to which this inequality holds. So applying this condition to this ux and uy, we will get uy x plus delta x, y plus theta 1 delta y minus uxy is less than epsilon 1, where epsilon 1 is some positive quantity, and ux x plus theta 1 delta x y minus, this is uy, ux x comma y modulus epsilon 1. Put this equation 2. This is from the definition of uniform continuity. Correspondingly, we will get, here my interval is del x, here my interval is del y and del x, del y less than delta, del y less than delta. Here my interval is the x comma x plus del x. Here my interval is y comma y plus del y. So correspondingly I will get this del x less than delta, this delta y less than delta. Now next I am going to put this value is equal to alpha and this value is equal to beta. One is alpha 1, another is beta 1. So next, let uy x plus delta x comma y plus theta 1 delta y minus bracket close uy x y is equal to alpha 1 and this equal to beta 1. Okay, this equal to one is alpha 1, another is beta 1. So next, u x plus theta 1 delta x comma y minus u x comma x comma y equal to beta 1. Okay, therefore using these two value 2 becomes If I put this equal to alpha 1, this equal to alpha 1, then this will be modulus alpha 1 less than epsilon 1. So modulus alpha 1 less than epsilon 1 and modulus beta 1 less than epsilon 1. That is, this will be beta 1 will be less than epsilon 1. Now from this I can write this equal to alpha 1 plus uy, and this will be ux plus theta 1 delta x comma y equal to beta 1 plus ux partial derivative of u with respect to x xy. So therefore 1 become, now 1 implies this one is this one, delta u equal to delta u is equal to what is delta u? That is delta y this one. That means delta y into alpha 1 plus uy. Delta u is delta y within bracket alpha 1 plus uy xy bracket close plus delta x then within bracket it will be beta 1 plus ux, beta 1 plus ux xy bracket close. So expand this, you will get uy. I am writing only uy, but whenever I write uy, this will be equal to uy xy. Okay, this is delta y plus alpha 1 delta y plus beta 1 delta x plus del ux delta x. Proceeding similarly, you can write proceeding similarly we get delta v. Proceeding similarly we get delta v is equal to by. Delta v is equal to by delta y, then alpha 2 delta y, beta 2 delta x. Okay, ux is bx, that is u will be replaced by bx delta x. Therefore delta fz by delta z will be my delta u plus I delta v by delta x plus I delta y. Now put the value of delta u and delta v. We will get delta u will be similar, exactly this one, only v is replaced by u, that is this that is uy delta y plus alpha 1 delta y plus beta 1 beta 1 beta 1 delta x plus u x delta x bracket close, this is for this value, plus I put the value of delta v will be delta v is by delta y plus alpha 2 delta y plus beta 2 delta x plus bx delta x bracket close divided by delta x plus I delta y. In the next step, use CR equation. Write it in terms of partial differentiation of x u with respect to x and v with respect to x. So uy will be minus px. CR equation is delta f by delta z is equal to CR equation minus bx delta y plus alpha 1 plus alpha 1 delta y. This is alpha 1 delta y. Here there is I alpha 2 delta y. So I am writing together, take delta y common, then it is alpha 1 plus I alpha 2 delta y. So this is alpha 1 plus I alpha 2 delta y plus again from here this right with this one, that is beta 1 plus I beta 2 delta x. Take delta x common, this will be beta 1 plus I beta 2. This will be beta 1 plus I beta 2 delta x. Then I will left with u x delta x, u x delta x, ux delta x. Write a remaining term. This is I v y delta y plus I partial differentiation of v with respect to y, that will be your ux by using CR equation, that is ux delta y. Okay, in place of vy I am writing ux delta y. This is I ux delta y. Again vx delta y, I vx delta y. Then write plus I vx delta y divided by del x plus I del y. Next, here you should write using CR equation, mean Cauchy-Riemann equation. What is Cauchy-Riemann equation? What is Cauchy-Riemann equation? Cauchy-Riemann equation is ux equal to vy and minus uy equal to bx. So here uy, so uy is replaced by minus bx, and here it is vy, so it is replaced by ux. So in the next step, this and this. This is delta x. Okay, this is delta x, not delta y. Delta x. Delta x. So from this and this, take delta x common, we will left with ux I bx delta x. Okay, from this term and this term I'm taking delta x common, I will left with ux plus I bx. Again this is minus 1. Minus 1 is my I square. So in place of this minus 1, I can write I square. So that from this and this, I can take plus I common, plus I common, plus I common. Then it is ux delta y common again. Within bracket it is I bx delta y. That means if I expand this one, I will get this and minus bx this term. So then in the next step, write the remaining term this and this. That is alpha 1 plus I alpha 2 delta y plus beta 1 I beta 2 delta x divided by delta x plus I delta y. Now take this term common, then I will, if you take ux plus I bx common, then within bracket I have delta x plus I delta y. So in next step it is equal to ux plus I bx delta x plus I delta y. Okay, then alpha 1 plus I alpha 2 delta y plus beta 1 plus I beta 2 delta x. Delta x plus I delta y. This which is equivalent to, which is equal to, if I write in fraction, that is ux plus I bx by delta x plus I delta y divided by delta x plus I delta y plus alpha 1 plus I alpha 2 delta y delta x plus I delta y plus beta 1 plus I beta 2 delta x plus I delta y. This cancel out. We will left with ux plus I bx. If I take to right hand side, then it will be delta f by delta z minus ux plus I bx is equal to alpha 1 plus I alpha 2 delta y by delta x plus I delta y plus beta 1 plus I beta 2 delta x by delta x plus I delta y. This one. That is, this term left as it is, this term left as it is. I will bring this term to left hand side. I will get this step, this step. Next, I will take the modulus. Next, I will take the modulus. Take the modulus both sides. Modulus of this, modulus of this, modulus of this, modulus of whole. Okay, modulus of whole, modulus of whole. In next step, it will less than equal to alpha 1 plus I alpha 2 modulus then modulus of delta x plus I delta y modulus delta y plus modulus beta 1 plus I beta 2 modulus delta x modulus delta x by delta x plus I delta y. Since delta x delta y are less than equal to delta x plus I delta y, modulus of this one. Okay, modulus of this one, that is modulus of this square will be square root of del x square plus del y square, which is always greater than equal to modulus of del x. So that means modulus of x is divided by this is always less than equal to 1. Similarly, modulus of y divided by modulus of x plus I delta y is less than equal to 1. This is from this. If my complex number is a plus I b, then modulus of z is this one, a square plus b square, which is a is always greater than a square, so root over a square. That means if you take some number, then it will be clearly visible. If you take 3, 4, then 3 square, 4 square will be my 5, and this 3 is less than 5. Okay, 3 is less than 5, and modulus of this one is always 1. So 3 is less than 5, that means 3 by 5 is less than 1. It will be easily visible when you take some particular number. So this portion is less than equal to 1. That means this is further less than equal to modulus of this one and modulus of this one. So use this. So in the next step, write this one. This is modulus. So this is the next step will be modulus of delta f by delta z minus ux plus I bx is less than equal to modulus of alpha 1 plus I alpha 2 plus modulus of beta 1 plus I beta 2, that is this, less than equal to this one. Here you should write, since delta x, modulus of delta x is always less than, reason I have explained you why, this one, and delta y less than equal to modulus of delta x plus I delta y. Okay, bracket close. Next, this is further less than equal to alpha 1 plus alpha 2. Here we have modulus of I alpha 2 will be modulus of I modulus of alpha 2. Modulus of I is my 1, because I can be expressed as 0 plus I, and modulus of I will be square root of 0 plus 1 square, that is root over 1, and root over 1 is 1. So using modulus of I equal to 1, we will get this way. plus beta 1, and by similar argument I have this one, and this value is my this one epsilon 1, and this value is epsilon 1. Here you should write one condition, that is alpha 2 is less than epsilon 2 and beta 2 less than epsilon 2. Okay, here our condition will be if alpha 1 is less than epsilon 1, beta 1 is less than epsilon 1 here, then in V it will be alpha 2 will be less than epsilon 2 and beta 2 is less than epsilon 2. So this value are my less than equal to less than epsilon 1 plus alpha 2, alpha 1 beta 1, alpha 1 beta 1, alpha 1 beta 1, epsilon 1 epsilon 2. This is epsilon 2, epsilon 2. This is again epsilon 1 plus epsilon 2. This is equal to 2 epsilon 1 plus 2 epsilon 2. Is it okay? Let us check again. Yes, this is epsilon 1, this is epsilon 1, this is epsilon 2, this is epsilon 2. It is correct. So this is 2 epsilon 1, 2 epsilon 2. Since epsilon is an arbitrary positive quantity, so difference between this is less than arbitrary positive number, that means this is equal to 0. So write as epsilon 1 greater than 0 and epsilon 2 greater than 0 are arbitrary positive quantity, therefore limit del f by del z tends to 0 is equal to ux plus I bx, that is f dex z. This quantity is equal to f dex z is equal to partial derivative of I bx. This exists, they are continuous, so this f dex z exists. That means hence fz is analytic. That means fz is analytic. That's the proof. Analytic function has the proof. With that, I would like to conclude. Remaining will be in the next lecture.